All right, so let's move on to question 3. So question 3, we have a road 1.05 meters long hanging from two wires A and B. A weight W is hanging from the road by a wire. The cross-sectional area of wire A is 1 millimeter squared and that of wire B is 4 square millimeters. Where measured from A, should the wire holding W be hung so that there is A, equal strength in the two wires, B, equal strain in the two wires, given that the Young's modulus for wire A is 2.4 times 10 to the power 11 pascals, and the Young's modulus for wire B is 1.2 times 10 to the power 11 pascals. Okay, so we have this diagram here. So we have the road, which is horizontal, with hanging from two wires, wire A and B, wire A being on the left and wire B being on the right. And we also have a weight W being hung at point C right here. So we want to find the distance X. Okay, how far should this W be from point A so that we can have equal stress in both wires? And also, how far should this weight W be from point A so that we have equal strain in the two wires? Okay, so we are saying let A and B be the areas for wires A and B respectively. Let also AC be equal to X, okay, and that AB equal to 1.05 minus X. Okay, just a correction here. I think this one has to be CB and not AB, so we have CB. Okay, so let CB be equal to the length minus X. So we have that stress in A will be given by the tension in A divided by the area of wire A. Also, the stress in B will be given as the tension in B divided by the area of B. So if we are saying the wires must have equal stress, then we are saying that the tension in wire A over the area in wire A must equal to the tension in wire B over the area of wire B. If we work this out, we cross multiply, we will discover that the tension in B is 4 times the tension in A. Okay, so the tension in B is 4 times the tension in A. So now let us consider the torque about the point C of this rod. We know that since it's held by two wires in equilibrium, the sum of the torques must equal 0. Therefore, we have tension B, which is the force, acting or rather perpendicular to the length minus X, and also tension A perpendicular to the length X must equal to 0. Okay, you have these diagrams in your tutorial sheets, so just look at the system, then you'll be able to know why or how I'm obtaining these tensions, or rather the torque. Okay, so we know that TB is 40A. We substitute, we'll have 40A multiplied by the length minus X minus TA times X equals 0. Okay, so we continue, we work this out. We are going to have 40A multiplied by the length minus 5TAX equals 0. So from this we are able to obtain the value of X as 0.84 meters. Okay, Therefore, if the two wires are to have equal strength, the weight W must be hung 0.84 meters from point A. Okay, so that is how we for equal stress. Now we go to the equal strain. So we know that strain is given as stress over the Young's modulus, stress being the force over area and our Young's modulus there. Therefore, we know that the strain will therefore be given as force divided by the area times the Young's modulus. So now, if we are saying equal strain, then we are going to have TA over A times YA equals TB over B times YB, right? So now we are saying TA, we don't know the value of the tensions yet, and we know the area as well as the Young's modulus for this one, okay, being equal to the tension in B divided by the area times the Young's modulus for B. Okay, so we cross multiply there. We're going to find a relationship which shows that TB is twice TA. Okay, so TB is 2 times TA. Again, for this case, we consider the torque about the point C, just like the case for the equal stress. Therefore, we'll have that the sum of the torques about the point C is going to be 0. Okay, so we'll have TB perpendicular to the length minus X again, minus the clockwise torque, which is TA perpendicular to X, giving us a 0. So we know that TB is 2TA. We substitute that, we have 2TA multiplied by the length minus X minus TA X equals 0. Okay, so we work through that and we are going to find the value of X as 0.7 meters from A. Okay, so we are saying that the weight W must be hung 0.7 meters from A so that the two wires can have equal strain. Okay, so we proceed now to question 4. Question 4, we have two parallel and opposite forces, each of 4,000 newtons, are applied tangentially to the upper and lower faces of a cubical metal block 25 centimeters on each side. Find the angle of shear and the displacement of the upper surface relative to the lower surface. The shear modulus for the metal is 0.80 times 10 to the power 11 pascals. Okay, so we want to find the angle of shear as well as the displacement of the upper surface relative to the lower surface. All right, so I suppose you know what is happening to this cube. It's like one is pulling from the bottom towards the left and another force pulling from the top towards the right. So it's going to bend, okay, making an angle. The top part is going to move or shift towards the right, okay, relative to the bottom part. So now we want to find the angle of shear, and we know that the shear modulus is given as stress over strain, which is force over area divided by elongation over the original length. Okay, so here we can find an expression for the extension, which is the displacement, that the top part will differ with the bottom part. Okay, so it's more like the top part is going to shift towards the right and the bottom part to shift towards the left. Therefore the displacement is going to be given as the length times the force divided by the shear modulus multiplied by the area of the cube. So the area is L squared, which is 0.25 meters squared, giving us 6.25 times 10 to the minus 2 square meters. And once we know that, we are able to find the displacement as Okay, so we simply substitute these values that we already have. Therefore, the displacement will be 2.0 times 10 to the power minus 7 meters. Okay, so this is how far the top part will go to the right relative to the bottom part of the cube. Okay, so this is the displacement. So now to find the shear angle, this is the easiest part. Okay, so the tangent of theta giving us the displacement divided by the length. Okay, so theta is simply the tan inverse of that, giving us an angle of 8 times 10 to the power minus 7 degrees. Right, so this one was a quick one. Yeah, so there's nothing much to do here. Okay, nevertheless, at least we are proceeding. Let's go to question 5. So question 5 here, we have a glass tube bent into a U shape, and water is poured into the tube until it stands 15 centimeters high in each side. Okay, a 3 centimeters column of alcohol is slowly poured into one side. The two liquids do not mix. How far will the water column in the other side rise, given that the density of alcohol is 720 kilograms per cubic meters and that of water is 1000 kilograms per cubic meters? Okay, so here the principle that we have to consider is the Pascal's principle. The change in pressure of column 1 must equal the change in pressure of column 2 according to this. Okay, knowing that the pressure is going to be the density of the liquid times G times the change in the height. Okay, therefore we are saying density of liquid 1 times G times the change in height of column 1 is equal to the density of liquid 2 times G times change in height of column number 2. Okay, so we have the densities, we have the value of G, and we want to find the change in height of the second column. Okay, so we know that the first column will change by a height of 0.03 meters. So we substitute those values into this expression, and we're going to obtain the value, or rather the change in height in the column 2 as 720 times 0.03 divided by 1000. Okay, these are just the values for the densities and the change in length of column 1, giving us the rise in column 2 as 2.16 centimeters. Okay, so if this is the change, or rather the total change in the columns, then for each side it's going to be this change divided by 2 columns, meaning that on each side the increase will only be about 1.08 centimeters. Okay, so that is how high the water column will rise on the other side. Right.